crazy.
Questions before class?
You don't feel like I'm so mandatory.
Could you define what's the most proper definition of realism? Would that be starting from you know that you know things versus when idealism is when you
So, question here on the homework. So the question, Mr. Rudman is asking really the best understanding of the relationship between philosophical idealism and realism. Read that part of the text. Anybody give a try? Yes, ma'am.
Idealists believe that everything is a mental construct, and realists are like, no, things exist. You can feel them, you can sense them, you can touch them.
And you could know them. Right, so that's good, that's pretty good. So an idealist, he believes, it's a belief, it's not really a science. He believes that we can only know our ideas. It's a belief. They can't even prove this on the basis, it's not even a self-consistent belief, but it's a common belief among many scientists. The realist knows that things exist independent of ourselves. And you can know them. In fact, you can know them down to even what the essence of those things is. You can understand the essence of these things around you. So that's a more precise, succinct definition of the relationship. Yeah, good question. Any other questions? We've got about a minute before class starts. Anybody listen to the Zoom recordings of the class by any chance? Somebody listened and said that, did you have any trouble hearing?
not the first one I didn't.
Okay. Okay, please, please check the second recording, the audio level. At the beginning, I was experimenting with the microphone, but then once the lecture started, I stopped that. So at the beginning of it, right at the very beginning, like talking before class, the audio level might not be real good, but once the lecture starts, it should be okay. So please be sure to check that. Let me know. Somebody said they listened to the second one, they had trouble with the audio for some reason. Okay, so there's a exam in class on this basic material on Wednesday here in class. So you come, we'll do the exam. And so we're going to do a little review and some new stuff, some additional stuff here today. Okay, so I'm just going to go alphabetically this first day and give you a chance to help us review. So the principle of non-contradiction, Mr. Bava.
Principle of non-contradiction.
Yes. Say again?
Can I read it off my paper?
Okay. Can you do it without reading it, or?
Not entirely, but it's if I remember correctly, something cannot be and be at the same time.
And in the same way.
In the same way.
Good. Okay, so memorize that. That'll be on the test.
Oops,
So
is this test also going to be like memorization like last time?
memorization like last time?
Right, like last semester I was like completely just memorizing word for word what the definitions were.
Yes. Yeah, there will be that. Yes. Yeah, I know that you've been encouraged in some classes, maybe in the past, to kind of rephrase things in your own wording. That's not what I want. This is physics, it's precise. This has been worked on very precisely, and you're learning that. It's not the end goal to memorize stuff, but it is an aid to your understanding. It's the beginning of understanding. If I ask you to write, we will study Schrodinger's equation here in this class. You're going to learn what all of these symbols mean. Okay, and I ask you to write Schrodinger's equation. I don't want you to put Schrodinger's equation in your own words. I don't want you to start rewriting. Well, I don't like H bar is always on top of the M. Why don't we put this here? And the T, I don't know, let's call it something else today. I don't want that, right? And so it sounds funny when I say that about an equation, but that's the same thing with regards to these more fundamental principles. We actually know these principles better than we know equations because it's an expression of our common understanding of the world. We know things. This is what we know first, not our ideas, but things. That's what we know. And so this understanding is made rigorous and precise. And so that's why I want you to memorize things. You wouldn't be kind of thrown off guard if you had to, come on, close it, lock. You wouldn't be thrown off guard if I asked you to write the Schrodinger equation, right? And in fact, you would have memorized it by that point. Or if you didn't memorize, you'd have to work on memorizing. Same thing. It's not a lot. There's not a big deal, but there is enough because you'll be asked. You wonder yourself, what's a wave function? You might be working on wave function. What's a wave function? So these sorts of simple definitions for things that are really common, ordinary, are going to lead us to be able to be precise and to say things clearly and in a meaningful way. Because a lot of stuff that we talk about in physics, if we haven't practiced this, we haven't understood this, it comes out kind of like gibberish. If somebody's trying to explain quantum mechanics, and they can't use math, then it comes out like gibberish. It comes out really strange. Take an ordinary physicist, talk about anything else in the world, and they have like a normal conversation. Get them onto the subject of quantum mechanics, and they start talking gibberish. And that's because they understand it mathematically. In fact, it's not just equation first, it's equation only. That's all they know. And when they start trying to talk, if you can't use the equations, they start saying stupid stuff. So that's what we're trying to get away from. So these basic definitions are the beginning for you to be able to do that well. Okay, so like the principle of contradiction. Here's an example. Because this is a subject where you see a lot of strange things being said, right? That assignment you had before class to go look at popular articles about quantum mechanics should have highlighted for you. There's a lot of strange stuff that people say about quantum mechanics. That's not physics, but that's unfortunately the situation. And this is trying to fix that. Here's a sentence, or it purports to be a sentence. This sentence is false. Okay. Now that sentence can't be true. It can't be false. In fact, it's actually meaningless. It's actually not a sentence. It's a bunch of words that are thrown together, but it's self-contradictory. A statement which is self-contradictory really means nothing, in spite of the fact that it sounds like it ought to mean something, right? If somebody says these words, you know every word, you understand the meaning of this sentence is false. You have all those words you understand. If you stick them together in a certain order, and they're contradicting each other, so it's not even a sentence. It's meaningless. And what we're going to be doing in physics for realists is saying true sentences that mean things. And you won't be saying self-contradictory stuff. You'll understand quantum mechanics in a way that is completely self-consistent. You won't be saying stupid stuff like this. So that's like the principle of non-contradiction, right? Reality is not self-contradictory. Reality is self-consistent. Okay. So that's very important. So that's a long-winded answer, but it's an important thing to know about why I'm asking you to memorize certain things. And if you had this from the beginning in mechanics, things like impetus and mass and stuff, you would have absorbed that already, and it wouldn't be quite so strange to you now. It just takes time. It will take time. These are very important. Physics principles. Why does something move? That's really important. Okay, principle of causality, Mr. Bestman. Here's Mr. Bestman. There you go. Principle of causality.
It's the idea that everything has to cause.
Yeah, I want the wording. Give me the wording where it's wrong. Right? I don't want you rewriting Schrodinger's equation. What's your name, please?
Redondo.
Mr.
Redondo.
Mr. Redondo, please.
Things can't change themselves.
Yeah, you guys speak up louder.
Things can't change themselves.
Yeah, something cannot change itself. Okay, and he was close, but not quite there. Something cannot change itself. I think there's also nothing can change itself in the, I kind of like this, I was going to go change that. Forgot to do it. Something cannot change itself. I like better. Nothing can change itself. Since it's, I think it was in the write-up, I'll take either one. I kind of like the something cannot change itself because it's, I think, a little more clear. What is a substance, Mr. Bowman? Okay. You have that written down? Okay, can somebody help out Mr. Bowman? Ms. Moyer?
Something that exists independently.
Close, but not there. Yeah, what's your name, please? Mr. Green. Mr. Green, thank you. Something that exists by itself. Something that exists by itself. Okay. Isn't it interesting? Well, we'll talk about that in a minute. How about what is a property, Mr. Campbell? Okay, remember substance is something that exists by itself. Property, yeah, it's redundant.
So a substance is a thing that exists in another thing.
Yeah, property is something that exists in something else. Okay, get the wording precise. Substance exists by itself, property exists of something else, in other words, substance. Yes, ma'am, Ms. Moore.
So the wording will work if something exists in another substance? Like
No,
for-
something that exists of in another. Yeah. Parenthetically, I added, because there are only physical things exist either as a substance or as a property. Then if it exists in something else, it must be a substance. Right? So I'm adding that parenthetic. But the two definitions complement each other because they're two kinds of things. Substance exists by itself, property exists of something else. Okay, Mr. Chandler, categories of properties, please.
So there's it's QQ refers to quantity, quality, reception, action, receptivity,
Almost. So quantity, quality, what's the
relation,
relation? Then action
Action,
and
reception.
reception.
uh,
And then the poet.
place, orientation, environment, time.
Good. Excellent. Very good. You'll remember that your whole life. QQ barefoot. It'll come back to you. You'll be 60 years old. QQ barefoot. Okay. Let's see. Mr. Green, what is quantity?
With the wording from the sheet,
Yes.
extension, having parts
That's it.
outside of each other.
That's it. Having parts outside of each other. Good. Yeah. Extension and having parts. That's quantity. We're describing a fundamental attribute of physical things. They all have extension and have parts outside of each other. Okay, Ms. Hoffman, what is a quality?
It's the motor and resistance.
Good, very good. Okay. Did you guess that you were H after G, so you were gonna be quality, or are you that good? No, that's all right. So what's the main distinction between quantity and quality? Anybody? Yeah, Mr. Patel?
Quantity amounts.
Quantity amounts. Essentially, right? That's the essence of quantity amounts. Now, qualities don't essentially amount. That is, in essence, they are something that not amounts. So, color, for example, you get two red things put together, I don't get a redder thing. Great quantity of reds. That's an example. So quantity amounts. Qualities essentially don't amount. Now we're going to encounter some qualities that mimic that quantity. And I think somebody asked about mass. Oh, it was density. You were talking about density, but let's talk about mass. Because we talked about resistance to the impetus. If I get two things, put them together, it seems like I have a greater mass. But mass is a quality. Because the essence of mass is the resistance to the impetus, not the extension. See the difference? So some qualities they're so primitive that they resemble in some way quantity. But the essence of that which is resistance to the impetus, is not inherently something that ought to add together. Okay. So you had several hands. Yeah, Mr. Chandler? Campbell, sorry.
So the atom itself has extension.
Yeah.
But the mass does not.
Correct. Right. Exactly. Just like the color doesn't have extension. Right. The temperature is not its extension. Those are essentially different things, even though I can measure those things and produce a number by a measure. Makes it seem even more like quantity that way because I can produce a number. But the essence of what you're measuring is not quantity when you're talking about temperature or mass or color. Yeah, Mr. Rudd.
I wanted to ask you, Dr. Like, for example, we're talking about mass, for example, if you had a beach ball that's still there, and you had another ball, let's say on a lead or something, they're both of the same extension, so they both have a different resistance, their own impetus. Would that be an example of showing that mass is not?
Yes.
Thank you.
Yeah. Did everybody hear what he was saying? You could have two objects that had the same volume, same quantity, but one has more resistance to the impetus, has greater mass. Right? And to understand that, you don't think of mass as being its extension, because they have the same extension, but one resists the effect of the impetus more than the other. So that tells you your understanding is that there's an essential difference between quantity, extension, and the resistance to the impetus. Yes, ma'am. Remind me your name.
Miss Lindler,
Linda.
Allie, yes, sir. So you couldn't have quality without quantity,
Correct.
but could you have quantity without quality?
Well, you can only in your mind, right? You can form a kind of abstraction in your mind where you consider quantity by itself. And that's what we do in math a lot. We think about a circle and we kind of forget that circle is first the shape of a physical thing. And that's how you come to know shapes, is by seeing physical things and you understand their shape. Then we form an abstraction, which is to consider a circle as though it could exist on its own with no other attributes. Right? The physical things have other qualities besides, they have qualities. They don't just exist and they're just quantity only. So the answer is no, it can't be pure quantity. The physical things are not pure quantity. But mathematics is the trick that we do in our minds, this abstraction. So it exists in the mind that way, but it's not, doesn't exist that way in the world. Yeah. So it's a kind of existence, but it's not physical existence. Good question. Okay, Mr. Pragi. What is measurement?
It's a relation to quantity.
You understand measurement? I mean, when I saw that the first time, I thought, wow, that's really cool. I mean, I've been measuring things all my life. I never really thought about it. Really simple. It's a specific kind of relation, an analogy, and it's a specific kind of quantity number. So, I'm working on that definition. A more precise definition is a relation. It's an analogy. It's a number. But I'm working on it. So use the one that's in the write-up. So that's still correct. So let's see, Ms. Lindler, what are the 3 types of measurements?
Time, quantity, and quality.
Right. So what would be the first? You got them in the different order than I
Oh,
have.
yeah.
Which one is first?
It's quantity, quality, time.
Right, yeah, that's right. Quantity is first. It's always first in these things because we're considering nature we're viewing nature through quantity, right? And quantity is the base property. So quantity is the first understanding. And when we're making an analogy to number, a comparison, a relation to number, we're doing this link to the table, producing a number, it's quantity to quantity. When we're doing qualities, then we produce a number. But we don't essentially reduce the quality to quantity. It's still essentially different. There's a similarity, but in essence, they are different. Yes, sir.
So in your example with the 2 things that are red, they don't combine to make something redder. But when you apply that to it still is part of measurement, how do you justify that, I guess? I'm just trying to work out how, is it like how red something is, or measuring the amount of light or the wavelength or whatever that makes it red, or?
But we'll talk about wavelength, that'll come, but right now, just looking at something is better than something else. So some qualities vary in intensity. You see different intensities of red. And 5 is greater than 4. So we'll start assigning that red is 5 and this one is 4. So we can make a gradation, an associated number. Okay, that's a measurement, but it's a looser form of measurement. It's a looser kind of analogy than the first kind of quantity to quantity, because we're comparing quantities and we're producing a quantity. It's all tight. This is a kind of an analogy, like we were talking about healthy. Fifi is healthy. Fifi's hair is healthy. Diet is healthy. Those meanings point back to the original meaning. So now we're pointing back to number. So there's a similarity between red having degrees of intensity. There's a similarity to a number, set of numbers. But that doesn't mean that color is number. And measuring it does not reduce it essentially to number. Okay, and if you were trying to explain to somebody who's blind what color is, it's challenging because they don't have that sense experience, and you can't just tell them it's a number, right? That wouldn't make any sense. You'd have failed. You have to find some other way. But one of the attributes of color is that it varies in intensity. Right? They're different shades, different colors. They vary in intensity. These are things you're describing to somebody who's blind about what it's like to see color.
Wouldn't it still be very confusing? Even
Sure.
if you told them like,
Yeah,
black is very intense.
that's right.
It's
difficult.
true, but what does that mean?
The only way you're going to succeed is to relate it to other sense experiences that they have. Smell, that they hear. And you can say, well, sounds, they have different pitches. Colors kind of like that in a way, right? You're making comparisons to things they do know. Right? And that's really what we're doing in physics. We haven't really thought about it because the equation, first physics, tries to skip over this basic stuff. Just learn to write equations. But really, to say something meaningful about an equation, you have to refer back to this basic stuff. And so this is how we're learning to understand first and then express to other people our understanding. And that's, we're going to use basic physics to be able to do that. And so that sense experience is always there. So did that help?
Yeah.
Good question. Okay, good. All right, and that's the that's the next point. Does measuring time essentially reduce time to quantity? No. You understand why?
Time is like the process of change happening.
Yeah. It's the duration of a change. Reveals to us change is happening. Some changes slower, some changes faster. But we're talking about change, and it's not extension, right? If I can walk back and forth, but I can't go back and forth in time. The left and the right-hand side of something exist at the same time, but past and future don't exist, right? There's now. Past is changes that have taken place. That's the past. And the future is what change will occur. Right? You can understand time in terms of change. But time is, you've learned to treat time on a number line. So I want to talk about that briefly here. Yeah, Mr.
So,
Campbell.
Time though, isn't that just because we're on limitation of being 3 dimensions? Because if we're 4 dimensions, wouldn't we look at this differently? Is that because we could step in and out of time?
Yeah, you're saying now something that really has less meaning, right? Because you're trying to invent something that doesn't exist. 4 dimensions. You live in 3 dimensions and things change. So what happens here? Let me show you how this works. Why it is that you're thinking of time as quantity. And there's a good reason why you started thinking that way. You've been trained to think that way. Let's take an inclined plane and we take a ball and roll it, let it roll down the plane. And now we're going to, how do we measure its distance? Well, we have the distance is the distance from some mark up here. And we have time. What is time? Well, I have a clock and I'm watching the second hand. And every second I mark the distance. Okay, I make a table. Time versus distance. And then we set both of them to 0 at the start. After 1 second, it's moved 1 meter. Say after 2 seconds, it's moved 4 meters. After 3 seconds, it's 9, something like this. Okay. And now we plot it. Well, actually, what we do is we make a bunch of points like this. And then we connect them by a curve. So we're actually making a set of individual measurements and then connect them by a curve. Okay, this is a thing which is like a history of what happened. And in that sense, you're seeing it all at once. But there was no parabola in the ball rolling down the inclined plane. We produced a shape. And we're even going to write an equation to describe this thing. As though time were a quantity. We can treat it as a quantity because it is a number in the equation. But time is essentially not extension. But you're going to, without even having discussed all of this, you just learned how to do this. And it kind of, after a while, it's kind of learn how to do it. You can manipulate these things. You really don't understand what you're doing in any really simple way. Can you see here how time has been made to look like quantity? But this is a history, but the ball, when it's rolling down, it's only at one time as it's coming down and then you keep watching it, it's another time and it's another time. Time unfolds, but it's not visible all at once. That's how time is not quantity. It's subtle, but once you understand it, I think it will help a lot because time, through exercises like this, we've come to think of it as an extension. Yes, sir, Mr. Silva, birthday boy. How'd it go?
Very well, actually.
All right, good. All right,
Thank you for
sorry.
So that phrase you just used right there, where it's like you can't view time all at once.
Right.
Can we think about that as like that's just another way I think about quantity? Somebody can kind of it all exists in one place at one time, one way.
The extension all exists at the same time, right? It has a left and a right hand sides that are outside of each other. They're different. They're here or here, all at once. That's true.
And I was also gonna say, like,
Mr. Miller, right?
Oh, more.
Morris, excuse me. I'm sorry. I apologize. I keep working. Go ahead.
Well, I was just curious, like, let's say for some reason that time were to just speed up like 5 times its normal duration, or 5 times shorter than normal, would we even detect that?
Well, so what would happen in that case? Actually, I'm going to talk a little bit about that at the end here. So
Because like, I would think our brains are like functioned as a way of saying like 1 second is 1 second, but if 1 second is like half a second, we say like half a second is half a second.
how do we experience time through change? Right.
Yeah.
And so
I'm
what
trying to
you're
say is like, we wouldn't experience any change.
right. Yeah. So, and in fact, there's a situation that hopefully we'll talk about today, which is in relativity, special relativity, where things are happening as a result of having impetus, a lot of impetus that makes things move really fast. So if we get to that today, I'll talk about it. It's not part of this course, but I did want to kind of bring it in if we have a chance. But I want to make sure to get through this here. So, Mr. Morris, can you tell us what is the imperiometric method?
Imperiometric method.
Yeah. 2 parts. Anybody help him?
Like, just active, possibly measurement.
Yeah, almost, but it's, what are the precise wording? Related to that, but not that. Yeah,
If 1 views the world through quantity,
good.
and then 2 captures that view in a symbolic system.
For the purpose of making a prediction about the experiment. View the world through quantity, taking this relation to quantity, this comparison to quantity, and capturing that in a symbolic system. So what is the essence of modern science? That's it. All this other stuff you've heard about hypothesis, controls, experiments, being empirical. There's nothing essentially modern about all that stuff because there were people doing all of those things before modern times. This essentially different step happened with Newton, where he applied the symbolic system to study motion of planets and was able to understand planetary motion by pushing symbols around on a page. That was new. That had never been done before. And carrying it to the extent these days, generation after generation of physicists has gotten more and more wrapped up in this to the point where all they can do is think about equations, and they think about the world through the equations. And it's hard, maybe at this stage, it's certainly hard for me to describe people who've had no physics at all, but it's also difficult for me to explain to newbies. Physicists who've done this their whole lives, that's what we think. We think equation, unless we work really hard to try to fill it out. So it's a kind of myopia. You have like these blinders on, and you ask them a question, and they can't use an equation. They start spouting gibberish because they don't know how to talk. They can give you equations, but they don't know what else to say. Okay, Mr. Nazarian, what is impetus?
It's the power activated in a body that moves at a constant speed in a particular linear direction.
Good. Only one thing missing. What's the category? Quality is in. Sorry. Power is in what category?
Quality.
It's quality. It's intrinsic to the body. It's not quantity. It's not its extension. Lots of qualities. Your ability to understand what I'm saying is a quality. It's a power. It's an ability. Mr. Parham, what is momentum?
It's the measure of impetus.
Which one are you? Thank you. Measure of impetus. Good. Very good. Nice and succinct. Mr. Patel, what is mass?
It's the reception of impetus.
Not quite.
Resistance to impetus.
It's the resistance to the action of the impetus. And what category is it in? Well, it's quality. So complete definition goes from generic to specific. So first we would say it's a property. Well, when we say it's a quality, that's implying it's a property. So we're saying it's a property. And then we're being more specific about the properties, the qualities, not quality. And there are lots of qualities, so we got to be more specific still. It's the resistance of a body to the action of its impetus. Okay, Mr. Redondo, what is force?
Force is the ability of a body to change the impetus of the
Good, what category? Quality, very good. Mr. Ricecroffer, kinetic energy. What is kinetic energy?
It's the measure of the rate of transport of the intensity of the.
Very good. Isn't that simple when you understand this, what kinetic energy is? You don't just have to answer 1/2 mv squared. That's kinetic energy. I don't know what it is, but there it is, right? It's so simple. It's not hard once you understand it. It really helps you to say meaningful things. Okay, and we talked about kinetic realism and idealism. Okay, so
Is kinetic energy a quality or a quantity?
it's a quality. It's another way of measuring kinetic activity. We talked about this kind of, so it's really a different measure of impetus than momentum. But really it's tied in, it's a measure of quality. Yes, sir.
I'm a little confused about how force can be added up, right? So how's it like, wouldn't that make it amount?
Yeah, there's another example, and momentum is the same way. If I take a bunch of bodies, put them together, I can talk about a total momentum. Adding like vectors, forces add like vectors. I can talk about it that in a certain way. But and there is a kind of resulting superposition of forces. For example, I can talk about the forces acting on this thing. Gravity is pulling it down, the table is pushing it back, those forces balance and in some way kind of counteract each other, so there's no net force acting on this thing because it just stays there. It doesn't have any impetus, it's not changing its impetus. Okay. But that's an example of this kind of these qualities that they have some similarity to number and extension, but they are not essentially number or extension. Because the gravity acting down on that thing is not an extension of anything. It's a force, right? I mean, that's the best word. It's not an extension of anything. It's an action by the plana on this thing. And the table is doing the same thing. It's pushing back. It's not the extension of the table. It's the action of the table to try to keep this thing from coming through. It's resulting from the integrity of the table to maintain its shape and not let something invade it. Okay, does that help?
Kind of. Then like, what would be an example of quantity?
An example of quantity, its length. It's volume. Really simple. That's all quantity is. Quantity is very small. But because it has the basic essential aspect of amounting, it's very useful for us to study. Because a lot of basic properties, even qualities, have a lot of similarity to quantity. Okay. And so in that sense, that's why the empiriometric method works so well if you study just basic properties of things. The empiriometric works less well when we're talking about other properties of things that are not so basic. For example, your ability to understand. Not so easy to represent empiriometrically. Not so living things are harder to find ways in which the empiriometric is helpful in understanding. Okay, so the empiriometric works really well in physics because we're studying certain basic properties that are close, similar in their relationship to quantity. And that's why the empiriometric works so well in the kinds of things that we're studying, because we're limiting ourselves to study things like change of place, things like that. Okay. All right, so we said the first two principles, things exist and things change. Okay, so it is some way could be another way. It is actually one way, potentially another. This more words that just describe the same thing. The existence and the changeability. Physical things are a combination of both. They act, but they are also potentially different. Act and potency. Physical things are a combination of those two, both act and potency. The potency is real. It's in the thing, but it's not an act of the thing. An acorn is potentially a mature oak tree. The potency is in the acorn, but the actuality is it's just the seed. But that's part of being physical. It's having that combination. It's always present in every physical thing in a lot of different ways. I'm actually here, I'm potentially over there. That exists, that potency exists in me right now, to be potentially over there. Well, how do you know that? Well, okay, I'm actually there. So I couldn't actually be here if previously I could not potentially have changed. Right? So how do you know that something has that potency? Well, if you watch it change and then you know it had that potency previously. Yeah, Mr. Campbell.
Is that where we get the idea of potential energy from that same concept of?
Yeah, but this is even more primitive than potential energy. But you're right. That's what that means. That's what that goes back to. This is even more primitive. It's an expression about the nature of physical things. They are all this way. And because they all do change, maybe not right now in every way, but if you wait long enough, it'll change. Okay, so act and potency. Okay, so change is a process. Notice that change was not on the list of categories. Change is not a property. Change is a process of what is potential becoming actual. So at any time, I have one place. But now I'm changing my place, but at any time during the change, I'm at only one place. So my change is not the property of me. And so strictly speaking, speed is not a problem. For that reason, because it's a rate of change. So speed was not in the list of properties. Okay, now we're going to use, there are different kinds of change, right? Yeah, go ahead, Mr. Silva.
Would rate be a quantity or a quality?
So rate is a mixture. You're measuring a rate of change of place, the speed. So a rate is not really itself a property of the body. That's the point. So it's changing place. So you want to know how fast is it changing place. So that's what that is. And it's kind of a mongrel thing because it's place that's changing, but you're also comparing time. So speed is not properly a property. So we talk about different kinds of change. There's a change. Remember, things exist, physical things exist as a substance or as a property. So we can talk about the substance changing itself, changing, not in terms of the properties of the thing, but as itself. So a squirrel dies. Squirrel doesn't exist anymore. It's gone. That's a change of substance. If I take a bottle of hydrogen and a bottle of oxygen, I mix it together and light it, I get a pop, and there's water vapor inside. That's a change of substance. We used to have hydrogen and oxygen, now I have water. I can put electrical leads into liquid water, and I can get gas coming off of the leads, collect the gas. I've now got hydrogen and oxygen. Passing electricity through the water, current through the water, I've decomposed it, and I now have hydrogen and oxygen. I had water before. It's a change of substance. But there are also changes of properties. Some show that there is than a change of substance, but sometimes properties change and the substance really hasn't changed. Like when I walk from one place to the other, my place has changed, but I'm still the same. Right? So that's a mere change of property. Yes, sir.
Is doing CPR a change of substance?
Doing CPR? What do you mean?
So like if they flatline, you bring them back, does that mean they're,
No, I don't think they were dead in the first place.
okay.
Yeah. But I mean, that's an interesting question, but you have to understand the basic principles. And to answer a question like that in a tough situation, that's not the place you try to go to learn about life. Right? To understand what life is, you don't want to work on this question, on those areas where we're not sure. You want to study those things you're sure is alive, right? And then understand the principle of life. And then by investigating it. And then you can tackle the question about things you're not so sure about, but you always have to investigate. You always have to go get experience and gather knowledge about the thing as it's happening. Okay? And that's true throughout all this. It'll come back when we're talking about atoms, because atoms are not something we have a lot of personal experience. We've got to talk about how to do that. Okay. All right, so there are older words for this, for act and potency, that are not so familiar, not used in this way these days. So I'm going to introduce you to these words, and these are the proper scientific meanings of these words. Not the words, not the way these words are getting used in modern conversation. The act is the form. Potency is the matter. This is the proper scientific meaning of these words. The form is what something is. Or you could say maybe using what something is actually. The matter is what something is potentially. That's not common usage, but it is the properly scientific meaning. But a lot of scientists will use matter to mean something else. In fact, matter can be massive body. A massive body is the same thing as matter. But that's a very imprecise and actually in conflict with the proper meaning of the word. The matter is the potency, and the form is the act. So using these words tricks you up because they're not like you're used to using them. Go back to act and potency, you'll be all right. Understand these words, no problem. Form and matter are not words that you're used to using in this precise way. Okay, so in other words, material, changeable, physical, all mean exactly the same thing. Plana. Is plana physical? Yes. Is it changeable? Yes. Can it be other than it is? Yes. It can change. So, I'm sorry.
Oh, no, yeah.
Okay. Now, plana is physical. It's changeable. It's not something you can directly sense very easily, right? I mean, you're sensing the properties of the plana, though, when you're looking through here. So you're not made immediately aware of it, but when you think about it, it must be the property of something that I'm looking at. So our senses connect to the properties. We don't directly sense the substance, we sense the properties. Okay, so here's our intellect led by the senses. The senses connect to the properties, which are determined by the substance, what the substance is. If it's gold, or if it's water, or if it's you, the substance determines the properties to be the way they are. So the substance makes the properties to be what they are, but the senses connect only to the properties. They don't directly sense the substance. You sense only the properties. And the senses feed the intellect. And the intellect is able to understand the substance, but it's this very indirect route. It's a bit of a challenge for us, but it's the only way we've got. You have to use your senses. But you can come to know what the thing is. But you have to use your senses, you have to use your intellect, and to understand the substance that is within. It's gold, it's not water, it's gold. Okay? But the properties themselves are not the substance. They are the sensible aspects determined by the substance to be the way they are. Okay. All right, so there was a question. I'm not sure I'll get finished this one, but there was a question which Mr. Morris was asking about amounts to relativity. So we have a hockey puck on ice here, we get it sliding, and we say, well, as a result, it's sliding. I can see it sliding, so I can deduce that it has impetus. I can't see the impetus directly, but I can see the effect. Some of the properties that I can't directly sense, but I can see the effect. So I can deduce it has impetus. But now let's move all of this onto a railroad car. Let's get the railroad car moving, and then we'll do the same thing again. In fact, it's hard for me to tell if the railroad car is moving uniformly. It's hard for me to see any difference. In fact, let's close the railroad car so I can't see out. I might not be, how could I determine that it's moving? Is there anything I can do, either with this hockey puck on ice or with cannonballs or rotating things, anything, any experiment I can do inside that would tell me that I'm moving? No, now that's interesting because that says something about the change that's occurring. So substances with impetus still behave in the same way as though they don't have impetus. Makes it difficult to determine in a railroad car with the windows closed up whether you're moving or not. As long as the motion of the railroad car is uniform, has impetus, it's not changing. Can't tell. The only way to tell is to open the window and look out. All right, now this has led people to a lot of confusion because they want to say that there is no such thing as motion. There is no such thing as rest. They are all the same. Rest and motion are the same. But that's a violation of the principle of non-contradiction. Something is both at rest and moving. That's a contradiction. That's a misunderstanding of relativity. Okay. And there's a kind of a strange thing about it because there exists radiation coming in from outer space called the cosmic microwave background. Heard about this? Yeah.
Like, how should I say it? Basically, is it do they pick it up and they are able to see the universe as it was previously, like a long time ago?
Not exactly. No, it is a relic of something that happened a long time ago, but it's not so that you can visualize something, make an image from it. So yeah.
Is where you're talking about that famous picture where it's like all the universe and it's like all the colors and stuff?
Yeah, that's right. So microwave technology was developed during World War II, radar and radios, high frequency. So this part of the spectrum was being understood, and they were making radio detectors that they pointed up in the sky, trying to get radio signals from sources outside. So I'll tell you the story in brief. Maybe we'll finish it on Wednesday before the test. So they pointed these radio telescopes up into the sky, and they kept getting signal, and they kept trying to eliminate sources of radio waves, some of which was terrestrial, right? Radio stations were around. Then there is natural sources in the atmosphere producing radio waves that happen. like that. So they had to try to eliminate all of this. And they found that pretty much no matter what direction they pointed it in the sky, once they eliminated the terrestrial sources, they got something, a background. It's a background signal. Didn't matter the time of day, didn't matter where the Earth was in its orbit, whether it was nighttime, daytime, it's all the same. That kind of surprised them because they were hoping to find objects in the sky that would emit radio signals that they could study like astronomical objects. And they found some of those, but they found this background in every direction. This is back in the, I guess, late 50s, early 60s. So they finally traced it down to that it's present in space. And the thinking now is that it is a kind of echo or remnant of the Big Bang. That the radiation from the Big Bang is still with us, but because of the expansion of the universe, it's cooled way down. And it has a spectrum that's like a temperature. Something a body with temperature is very cold, 3 degrees. Remember correctly, 3 degrees Kelvin. Okay, precise measurements have now been made. What a redshift is?
Yeah.
If you move towards light, the color shifts blue, changes color. You move away from the source, it shifts red, gets red. The faster you move relative to the source, the more the change is. Same thing happens with this microwave signal. So they have measured now the motion of the Earth relative to this cosmic microwave background. And they've determined the direction of the motion of the Earth. So they're on top of this background, which was the same in all directions, there is a small amount of redshift depending on where the Earth is in its orbit. And the Earth is moving relative to the cosmos. So this big radiation from the Big Bang sets up for us a way of determining motion relative to the cosmos. Okay. So that establishes for us, because we can look out from the room, we can determine our motion relative to that background. And that establishes for the entire universe a frame of reference, which is the reference frame of the universe. Everybody in the cosmos, is anybody else out there, can do the same experiment and figure out how they're moving relative to the background, the cosmic background. Okay. So that doesn't violate the principle of relativity, which is if I close the windows, there's nothing I can do in here that will tell me whether I'm moving or not. In fact, so I can set up all kinds of experiments in here. There's no way to do it. I can't tell, but I can look outside and see the motion. Okay. So there is, in principle then, a way of determining, and in practice it's difficult, but determining I'm at rest in the universe. I have no influence. That is possible. In practice, it doesn't matter in terms of the physics that we do, whether the room we're in is absolutely at rest in the universe or is moving. Doesn't matter. The physics comes out, the experiments come out the same, unless you're looking at the cosmic microwave background. Okay, so that's a pretty short answer to, but that's where that discussion about relativity. You do all this on a railroad. Say again?
I was talking more about like time.
Okay.
Like,
so the effect of all of this, and this is treated in the last chapter of the mechanics book, the effect of all of this is a body with impetus is shortened along the direction of motion, but all bodies in the room are shortened by the same amount. And also time flows more slowly, that is, change occurs more slowly. Measured by somebody who's in a different, say outside of the train car, we're a small train car instead of a bigger train car, and we're moving inside the big train car, we can compare results of measurements. These things are happening as a result of having impetus, alters the body in this way. So the beauty of it is, if you understand this by reading chapter 10, a lot of what is called paradoxical stuff in relativity is not paradoxical. You really understand what's going on. So if you really want to understand relativity in a way that's not paradoxical, pick up the mechanics book. In the last chapter will help you. Okay, that's just a kind of an addition. So we'll have the test on Wednesday, start